will explain to you.
Okay. Hello everyone. I'm Viren Liu from Alibaba Group. Today I will work private set operations from multi-query reverse private membership test. So MQ-RTMT. So this is a joint work with Yuchen, Mingzhang, Congzhang, and Minglang Deng. Our presentation will have 5 parts. First part is about the background and contribution, and then the PSO framework from MQ-RTMT, and then the construction of our MQ-RTMT. And next is comparisons and experiments, and finally the summary of this work. So let's come to the first part, the background and contribution. The private set operations allows 2 parties to perform secure computation on their private set. And PSO includes a private set intersection, PSI, and private set union, PSU. And PSO also includes private computation on set intersection, PCSI, including the canarity sum, and a general computation. There are a wide range of applications of PSO. For example, we can use PSI for private serving location sharing, private contact discovery, and DNA testing and party matching. Certain real-world applications, such as measuring the effectiveness of online advertising, would only require aggregated information based on the set intersection. So that is where we need to use a PCSI. And PSU has also a lot of applications. For example, the IP blacklist and vulnerability data aggregation, the private DB supporting full join, and private ID. And PSI has been extensively studied in the last 2 decades. And for the abundant setting, there are very famous works that achieve linear complexity and almost as efficient as in-square hash protocols. For the abundant setting, we always use a fully homomorphic encryption, and this work achieves sublinear complexity of large size. However, in shape contract, the study of PCSI and PSU are not satisfying. For PCSI, some work achieves linear complexity, but the concrete efficiency is 20 times lower in timing and 30 times more communication cost than PSI. And for the PSU, there are works that have a super linear complexity, and there are works that achieve linear complexity but not strict. And the performance is concretely 20 times slower in timing and 35 times more communication than PSI. So I want to achieve 3 goals. The first one is different PSO protocols are based on different approaches, require much more engineering effort and maintaining cost. So the first goal is we want to have a unified framework of PSO. And second, there is a huge efficiency gap between PSI and other PSO protocols. And so our second goal is to want to have efficient instantiations to close the gap. And third one, after around 40 years, DHPSI is still the most easily understood and implemented one among other PSO protocols. But surprisingly, no counterpart is known in the PSU setting. Existing protocols are very, very complicated. So our third goal is to build a PSU based on DDH that is as simple as DHPSI. So we raised our following 3 questions. Is there a central building block that enables unified framework of PSO? How to give instantiations with optimal complexity and good concrete efficiency? And can the DDH assumption strike back with efficient PSU protocol? So our tool is to MQ-RTMT. So let's review the PSO framework based on the MQ-RTMT. We can build PSI using MQ-PMT. In the MQ-PMT, the server input is a set Y, and the client input is a set X. And the client will get an indicator bit vector representing whether its element is in the set Y or not. So if the element is also in the set Y, it means that the element is in the intersection, otherwise it will not. The problem is that the client knows both XI and EI. So it's not suitable for protocols that should hide the intersection, such as PCSI and PSU. The solution, in fact, is MQ-RTMT. R represents reverse. So we let the server learn the EI, while the client only learns the XI. That is his input size. It definitely learns the XI. And the server learns EI, each EI representing whether the client's element in X is in his own set Y. So the intersection information is then shared, so it's suitable for all PSU protocols, for all PSO protocols. So we can use MQRPMT to build PSI coupled with OT. And compare with, we just let the receivers additionally obtain the intersection of X and Y using the OT. But compared with the standard PSI protocol, if we want to use MQRPMT to build PSI, we will let the sender to additionally learn the intersection size of intersection size. And MQRPMT also yields PSU coupled with OT, but in this case, we need to leave the indicator bit vector E in the OT's procedure. MQRPMT also yields PSI car sum coupled with OT and masking trick. And finally, MQRPMT yields PSI car secret share coupled with OT and masking trick. So the key point or the key question is how to construct MQRPMT. So that's is our main contribution or construction of our MQRPMT. To do that, we first formally define two standard properties for the key function f, the composable and commutative. Here's the definition of our first tool, the commutative weak PRF, CWPRF. We say that f is a CWPRF if it satisfies the weak pseudo-randomness and commutative property simultaneously. Somehow we might think that why we just define the weak pseudo-randomness instead of standard pseudo-randomness, because commutativity denies standard pseudo-randomness, and here we give a tag to break the standard pseudo-randomness. And we define that because we want to use a DDH. We want to use a DDH assumption to build a CWPRF. So the construction is almost the same as the DHPSI. It's really simple and the proof is very, very simple. But we want to note that CWPRF is the right cryptography abstraction of classic DH function. But in the MQRPMT, we want is the standard pseudo-randomness. So the solution is to amplify the randomness via the hash. So we have below we have a relationship between these tools. So we use the random oracle hash function H to do the randomness application. And then we use the CWPRF to achieve or target standard pseudo-randomness. Then we can once we have the CWPRF, we can easily build MQPMT. But here we reverse the roles of the sender and receiver to compare with MQRPMT later. And we can see that this construction is almost the same as the DHPSI. But we will note that in the last procedure, we need to allow the sender to send the omega by preserving the order of the set Y. But this order preserving encoding will reveal the intersection. So the solution is pretty simple. It's extremely simple. It's just let the client to send the encoding in a permuted order. But we will allow the client to save its permutation. In this way, we will let the server just get the indicator bit vector without having the relationship between his element Y and the result in omega. And we mentioned that we can have we can do it more space efficient, that is using the Bloom filter. Another tool to build MQRPMT is to use the so-called permuted OPRF. And here is a standard OPRF. Also, we reverse the roles about the standard and server to compare with our construction of MQRPMT. And we also know that in order to make the OPRF to build the PSI, we'll also need to order preserving encoding. And this order preserving encoding will also leak the intersection. And the solution is also pretty simple. We just send back the permuted encoding so that we will hide the intersection. And based on the permuted OPRF, we will get our second construction of our MQRPMT. And we observed that DDH-based CWPRF is actually a CWPRP, so we can use the DDH-based assumption or the DDH style construction to construct our POPRF. So the construction is also very simple. It's almost the same as a variant of the DH-PSI. And we just let the server to blend its elements using his secret S, and we will let the the client to use his OPRF key to to encrypt it again, to encode it again, and finally we let the server to deblank the secret S and gets OPRF result. And here we give comparisons between these two constructions, between the CWPRF and the POPRF. We can see that we can use the X15519, the 25519 to construct CWPRF, but we cannot use that tool to build POPRF. Also, we can use blown filter optimizations using CWPRF and not OPRF. Therefore, the POPRF-based MQRT is more of a theoretical interest, but we mentioned that it can be viewed as a counterpart of OPRF-based MQRT construction. And so far, we only know how to build the OPRF based on assumptions with nice algebra structure like DDH, but not from fast primitives that is used in the PSI, such as OT and or VOLE. So this somehow explains the efficiency gap between MQPMT and MQRTMT. So given the efficiency gap between the PSI and other PSO, it's triggering to study the connections between these two tools. So towards this goal, we made a first step. We first abstract a category of MQMT called sigma MQPMT. And we abstract sigma MQPMT with reusable and context-independent and stateless test properties. With these properties, by using the permute and test approach, we can tweak sigma MQPMT to MQRTMT. But in this construction, we will additionally review the intersection size to the client. So we make a star here. So it is not a standard construction for the MQPMT. So using this abstraction, we can translate the category of PSI to PSO. And we believe we make an initial step towards establishing the connection between MQRTMT and MQPMT. So this is a summary of our main result. There are really a lot of tools. So please download the slides you want to study. And if you want to get more details about this, please refer to our paper. And finally, the comparison and experiments. This is very interesting. We implement our PSO framework by first constructing an easy group DDH-based CWPRF, and then based on the CWPRF, we construct our MQRTMT, and then we have our PSO framework. We use two curves. The first curve is NIST P256. We will mention 3 points. The first point is the hash to point operation is very, very expensive. It's almost the same as non-fixed explanations. And the point compression half the combination cost, but point decompression is very, very expensive. And also, we know that OpenSSL provides a similar implementation for all platforms, and that's a reason why we use the NIST P256 instead of other curves. And we also use a curve 25519, and it has a lot of advantages. It has no backdoor, it's fast implementations, and it is secure against the channel attack. And it allows explanations with only ACK coordinates. So it has the communication while there is no point decompression. And finally, any 32 bytes array can be represented to an ACK coordinate of a validity point. So hash to point operation is almost free. So for the first time, we use curve 25519, fully as leash is power in PSO. And by leveraging optimized implementations, the performance is even comparable with symmetric key operations. That's comparable. It's not so comparable, maybe 10 times slower or something. Yeah, but it's almost, it can be compared between each other. And we implement all the primitives in a unified library. And here we show the development and test environment. And we test various PSO protocols, include MQRTMT, PSI, PSI card, PSI card sum, PSU, and private ID. And we test the functionality, the computation cost, and the combination cost. And here are some really a lot of tables. I will skip just show the result. Or MQRTMT achieves strict linear complexity and is very, very high parallelism. And for 2 to the 20 scale, the time is just less than 50 seconds. And using full threading on the laptop, and the communication is just less than 60 MB. And I also implement the PSI and compare the existing DH-based PSI implementations. And we find that, compared to the existing DH-PSI implementation, the time speed up about 5 to 25 times. And we also have the PSI card sum and PSU's performance. And finally, summary of our work. Because of the time limitation, I just want to mention that you may think that our contribution is our construction very simple, but we do not take shame in the simplicity of our construction because simple is elegant and extremely efficient. So that is my presentation, and please feel free to visit the website to see the full version of the paper. And I'm very happy to answer any questions. Thank you very much. Maybe it's so simple. So no questions.
You have mentioned that they have efficiency gap between the different kind of PSI, because you see some PSI using OPS, and OPS significantly slower than other kind of constructions.
Yeah.
So can you explain why? And why do you look at pretty slower than OP construction?
Okay. Use the microphone, maybe. Yeah, thanks for the question. The question was, there's a gap between the PSI and reverse PSI, especially for some PSI that are very efficient. So can I get some explanation why they are efficient?
Yeah.
The reason is that I personally believe I have to say that I implement almost all the PSI protocol, and for the most efficient one, they use the so-called batched OPRF. They run OPRF in a batch to try their best to reduce the asymmetric operations. But if you use the batch OPRF, I think it's hard to do the permutation, okay, in the construction. So I think that's the reason why we cannot get efficient PSU or PSO protocols compared with existing PSI. We are still trying to find ways to do that. I think that is the main reason. Yeah.
So do you have any ideas how you could speed up or bridge that?
Currently, I do not have any solutions about that. I think it's a really open problem to have a more efficient PSU.
So before we proceed to the next talk, I want to make an announcement. So after this session, there is one more session. And before heading off to lunch, please wait. There's going to be a group photo at 12:30. So please join the group photo.
Just the back.
Yeah, just there at the back. So please don't leave. So we'll move to the next talk. So the next talk is strongly multiplicative secret sharing schemes with repairing adaptability. And the authors are Daniel Scorto, Ivan Chuavinata, I said it right, and Yoping Shane, and Ivan is a speaker.
Okay, so thank you for the introduction and thank you for the opportunity to briefly share about our work titled Strongly Multiplicative Secret Sharing Scheme with Repairing Ability. This is joint work with Daniel Escudero and Professor Sing Chao-Ping. So this is the overview of my presentation. First, I would like to briefly give some information and introduction regarding the setup of our work. The main technology that we will be using is a RAM secret sharing scheme. As we all know, secret sharing scheme can be seen as a pair of protocol share and recover for n parties. And it also comes with this pair of sets called access structure gamma and F. So in here, given the secret, the share protocol will generate the share to be distributed to n parties. And for the recovery protocol, it works in two different ways. For any authorized subset, as in gamma, if we collect out of the share, this one, the recover protocol can help us to recover the secret correctly. On the other hand, for the collection of shares from a forbidden set S from F, this one will give us no knowledge about the secret. So in our work, we are discussing about this TRN web secret sharing scheme, which comes with 3 parameters, T, R, and N. R is called R recovery, reconstruction threshold. And in here, it is we can see this by having the authorized subset to contain all the subset of size at least R. On the other hand, this secret sharing scheme is T private, since the forbidden subset contains any subset of size at most T. So just some observation, if R equals to T plus 1, then this one reduces back to the more generally known and used threshold secret sharing scheme. Now, secret sharing scheme possess many different properties, but in our work, we are particularly interested in this properties, linearity, and multiplicativity. So in here, linearity just means that the set containing the factor formed by the secret and all the possible valid shares of it forms a factor space. So in other words, this one can be seen as given a valid share of 2 different secrets, linearly combining the 2 secrets in element-wise manner can give us a valid share of the secret obtained by using the same linear combination to the 2 secrets. Next, for the multiplicativity, a secret sharing scheme is called multiplicative if a valid secret sharing of S times S prime can be calculated from the element-wise product of the share of the 2 secrets. Strong multiplicativity is just a stronger notion of it, where we require that the secret sharing scheme is T private, and this S times S prime can be recovered not only from this element-wise product, but only by n minus T entries of it. Now, the motivation behind why we are considering this secret sharing scheme with linearity and multiplicativity is we are interested in the application of it to multi-party computation. So as you all know, these are the basic setting. So MPC is a protocol that allows a set of mutually distrustful parties to securely compute a public function on private data, where the common design technique is to have the private data to be secretly shared and the computed function to be decomposed into circuit of addition and multiplication operations, where each operation is processed independently with the invariance that both the inputs and outputs are secretly shared. Now, take note that if our MPC scheme is very complex, then it may take a long time, and this will increase the possibility that some of the computing parties become disconnected or lost their share. So that's why this motivates us in trying to find out if it is possible for us to have a secret sharing scheme that can repair the share. Next, the property of secret sharing scheme that we discussed before, linearity and multiplicativity, of course, will help us in designing this kind of MPC scheme. More specifically, linearity allows addition and public constant multiplication to be done locally, while strong multiplicativity allows the calculation of the product of the 2 shared values. Okay, in here, we will be discussing a family of Xiaomi secret sharing scheme and its variants. So first, I would like to briefly recall what is Xiaomi secret sharing scheme so we can have the same notation. So we will be working on FQ, final field of Q elements, where Q is a prime power and Q is larger than n plus 1. And we will assume that T is the privacy threshold. Next, we will fix n pairwise distinct non-zero elements of FQ alpha 1 to alpha n. So given a secret, we can just choose random polynomial f with degree t such that the constant term is s, and the shares is simply f at this alpha I. So in here, some observation. First of all, using Laplace interpolation, it is easy to see that given the evaluation value of this function f at least t plus 1 distinct value, s is recoverable, while only having t of them, we will learn nothing about s. So in other words, this one is a linear T out of n threshold secret sharing scheme. Next, it is also multiplicative, and in fact, it can be shown that Xiaomi secret sharing scheme is multiplicative if T is less than n over 2, and strong multiplicative if T is less than n over 3. So for the rest of this presentation, I will assume that any secret sharing scheme is in the form of this Siamese secret sharing scheme or its variant. So in other words, we will have the distinct non-zero evaluation point and the finite field and the generating polynomial f. Okay, so this one is the feature that we are interested in, which is how to share to repair the share. So suppose that we have, like before, we have a secret and secretization with to S1 to Sn using generating polynomial fx on evaluation point alpha 1 to alpha n. So suppose that somehow S1 is lost, this can happen maybe because the computing parties holding S1 crash or get disconnected during the computation. So a very easy way to fix this is to use a straightforward repair where all the parties come together, share their shares and to recover the secret and the generating polynomial f. And based on this, they can simply plug in x equals to alpha 1 to get S1. Now, although this repairing process is very simple, it comes with some drawbacks. First of all, it is easy to see that if all the parties come together and share their shares, that means that there's no privacy guarantee on the secret, generating polynomial or other shares. Although this seems to be scarce, actually it can be fixed by having just have the party to run a mini MPC protocol to jointly perform this computation. Now, the thing is, having this mini MPC protocol to be done, it comes with another drawbacks, which is if the privacy threshold is proportional to the number of parties, since we need at least that many parties to come together to generate and recover the secret, that means that the repairing process will involve at least proportional to the number of parties, which may become invisible when n grows. So based on this, it seems to be natural to ask if it is possible for us to have the repairing process to involve a smaller number of parties. And then this one is similar to the regenerating error correcting code, but it has some difference. Furthermore, instead of allowing any group of parties in repairing any kind of share, we also want to have this concept of locality, where, as you can see below, we want these parties to be grouped to smaller subgroup of size L, and the repairing process of one party only involves these parties, the parties from the same subgroups. So some discussion about this locality. So suppose like before, we have this group containing L parties and share repairing process only requires the involvement of L prime less than or equal to at least L minus 1 of the party inside the group. It is easy to see that this implies that the collusion of L prime parties can learn the share of any parties in the group. On one hand, it may not be that serious because there's no effect on the privacy of the original secret or the original generating polynomial. However, one of our requirements is that we don't want the share to be leaked. So that's why we want the privacy of the share, and this will violate that requirement. So because of that, the solution that we decide to use is that we assume that the adversary is static, which is a general assumption on the work on regenerating secret sharing scheme. And in here, we will assume that the corrupted parties are chosen before anything happens, and that the assignment of the party can be done afterwards in public. In here, we decide that the random assignment can be done in public, since the group and the party identities needs to be known in public anyway. So here we come with the natural questions that we are trying to answer. First of all, can we design a variant of Siamese secret sharing scheme that comes with a share repairing scheme, and it only involves a smaller amount of parties with some degree of locality? And second, can this be designed with security guarantee not only for the secret, but also for the polynomial and any other shares? And lastly, since we still want the secret sharing scheme to be useful in MPC, we want the secret sharing scheme to still have this multiplicative property and hopefully also strong multiplicative property. Furthermore, regarding this third question, we also have some objective that we want to achieve. We want the multiplicative property to be achieved with the threshold, the privacy threshold asymptotically close to what can be achieved by classical Sherman secret sharing scheme, which is n/2, close to n/2 for standard multiplicativity, and n/3 when it is strongly multiplicative property. Okay, so here are some existing results that has been done before. On one hand, there are a lot of works on repairable error correcting code, and it has been well explored, especially in the relation to distributed storage systems. However, we know that in this work, the main priority is on the recoverability of the data instead of its security. So that's why in most cases, the problem of security and multiplicativity are not considered. On the other hand, there's also a lot other work for secret sharing scheme. We have numerous work on the secret sharing scheme with multiplicative property. However, there's no consideration on the repairability. And there's also some works on repairable secret sharing scheme. But in most cases, since the technique that they use is non-linear, they do not provide multiplicative property. And for the privacy issue, they only provide privacy of the secret against passive adversary. Okay, next, I would like to discuss some possible naive solution that may answer all of our questions, its properties, and why we want to have a new consideration. So you may notice that actually it is easy to solve this by using two-step Sherman secret sharing scheme, where we have the N group to be grouped to M group is of size L. And then suppose that the secret is S, then we have the first step to generate the shares, intermediate shares for each group S1 to Sn with some threshold. And then for each group, they further share it again. So now in here, we can use just a straightforward repair just for the second level. And now in here, it only involves L users, and then it seems to answer all of our problem. However, we take note that there's some property here. First of all, about the threshold. So in here, after some careful analysis, you can find out that this lower bound and upper bound of the privacy and reconstruction threshold. So even when we only consider passive security with standard multiplicativity, in other words, the W is less than M/2, the gap is still OL. Although this one is quite good, where it can be constant with respect to N if the number of group is proportional to N, we would like to do better. Next, due to the simplicity of this two-step Sherman secret sharing scheme, there's a very weak relation between the evaluation point on the inside and outside of the group. Because of this, the guarantee for the reconstruction and privacy threshold becomes much weaker. Okay, so in here, because of this guarantee becoming weaker and the gap becoming bigger, this one is not really good because we may have less choice in setting the parameters. For example, if we fix the privacy threshold, the reconstruction threshold may be prohibitively high. Okay, lastly, we go to our proposed construction. So the main thing here is our work is based on this work on locally recoverable code proposed by Thamo and Park in 2014. So this one is the proposed construction. So we still have Q to be the size of the underlying finite field, and L is a factor of Q minus 1, where N equals to L times M. So in here, we will be using this subgroup of multiplicative group FQ star of size L and Q minus 1 and M of the cosets for the evaluation points. And the main point here is to define this GX such that it restricted to any of these cosets, it is constant, non-zero, and the constant non-zero is different for different cosets. And based on this G, we can define our shared polynomial on this F such that the requirement is S equals to F0. So now some general discussion on this. this one can be seen as a special case of naive two-step semi-secret sharing scheme with a more carefully chosen evaluation points. And we know that with a more general choice of evaluation point, it can actually be shown that it can be reduced to this finding this chi. And if our evaluation points are not chosen carefully, then the degree of this chi can be very high, and most of the time it will be equal to n. However, in here we can force this degree of chi to be L, which can be shown to be optimal. So based on this, we can have this result on the threshold. So in here, I think the main point is the last row. So we can see that with this more carefully chosen evaluation point, we have decrease on the negotiation threshold as well as privacy threshold, but the decrease here is much larger, so that we can observe that the gap is also decreased. So the change here can be seen to happen in any choice of parameters, and because of this, the gap are smaller in any case. For multiplicativity, in fact, we can have what we want to achieve, which is that for carefully choosing the parameters, we can show that it is multiplicative when t over n is arbitrarily close to 1/2, while it is strongly multiplicative when t over n is arbitrarily close to 1/3. Lastly, for the repairing scheme, so we can do similar thing like before, like the straightforward repair. However, in here, the mini MPC protocol only involve the same the parties from the same coset. Furthermore, we can show that the share privacy is statistically secure with negligible failure probability as long as the size of the group is proportional to ln n power 1 plus epsilon. Okay, I will conclude my presentation by discussing some possible feature research direction, in particular in its application in MPC. So we are interested to see if it is possible to design an MPC protocol that allows for competing parties to get disconnected and rejoin later. And to generalize it further, we also want to see if we can allow for newcomers. In here, we see that our work is can be seen as some initial step in such an effort in improving the efficiency, since now our repairing process only requires smaller number of shares. And lastly, as you may notice, previously we have this static corruption assumption, but it may be interesting to see if it is possible to remove this assumption. Yeah, that's all that I want to say today. Thank you.
Questions?
Yeah, great talk. I would like to, can you just briefly remind me what is the like motivation of your work there, since you are just it works like a secret recovery from the instead of repairing, since the repairing is like to me like the secret shares to be modified or be malformed. Since I think in this work you consider that you are gonna recover the lost secret shares, right? So I would like to hear more about your motivations, why this is really important or interesting.
Thank you for the question. So just to make sure that I understand the question, you're asking what is the motivation of this work, and what is the relation between repairing for the share? Is that accurate? Yeah. Okay. Yeah. So in here, I agree that in this case, our motivation is more towards, like as I mentioned before. Yeah, so since in MPC protocol, sometimes in here, because we need to process the circuit, it may take a long time, and sometimes some of the computing parties may get disconnected or just skip some of the step. So because of this, he will lose the share instead of having it to be changed. So corrupted here means that it's completely gone and we need to recover it again. So repairing in this sense so that he can rejoin later in the computation instead of it being maliciously changed.
Considering the repairing. Get rid of the repair, we get a better fund. If we do not consider privacy, we just only consider repairing. We get a better fund based on your consideration.
Thank you for the question. Again, we just want to make sure that I answered it. Your question is if we just ignore about the privacy concentration, what will happen to the threshold? Okay, yeah. So in here, actually, for our construction, the construction of the repairing process is somewhat independent of the construction of the secret sharing itself. So we are not we are not making the threshold worse because of this repairing process. Of course, if we just try to use different way of returning secret sharing scheme, I think it is possible, and there's also some other works on this. Yeah, so they have this, they have some of this result on repairable secret sharing scheme. But I think in here, yeah, so in here, some of them either do not consider the secret privacy or they just consider this. So I guess for this one, this one is the technique is a bit different, but it may be interesting to consider here if you don't want to consider.
Questions, please talk to Ivan at the session. Sure. Third talk. Third talk. So this is a talk on network agnostic multi-party computation revisited. And the authors are Nidhish Vimrajka, Ashish Chaudhary, Supreet Vardarajan, and Nidhish is going to speak.
Thank you for the introduction. So I'll be presenting our work on network agnostic multi-party computation revisited. So this is a joint work with my supervisor, Professor Ashish, and my colleague Supreet. So secure multi-party computation is a seminal work by Yao, which addresses the following problem. Consider a set of n mutually distrusting parties that are connected by pairwise channels, where each party has some private input. So the goal of secure MPC is to allow these parties to jointly compute some function on their inputs such that nothing beyond the function output should be revealed. The distrust in the system is modeled by an adversary that can corrupt up to any T parties in the system. And traditionally, MPC protocols are designed in two communication networks. The first is a synchronous network, where there is a publicly known upper bound on the message delay, and every message sent is supposed to be delivered within that delay. MPC can be designed in this network as long as up to half of the parties can be corrupt. And the another model is in the asynchronous network, where there are no such strict timeouts, but the only guarantee is that every message sent will eventually be delivered. So MPC can be designed here as long as up to a third of the parties can be corrupted. So the natural question is, does there exist an efficient MPC that tolerates up to TS corruptions in a synchronous network and up to TA corruptions in an asynchronous network, where the parties are unaware of the exact network type? So this has been answered in the literature by these works, given the condition TA plus 2TS less than n volts. But all of this works, they use some other kind of heavy cryptographic machineries like zero knowledge proofs or setup assumptions like threshold homomorphic repetitions. So in this work, we try to answer the same question with the same bound, but without use of any heavy cryptographic primitives. So we instantiate our MPC protocol using the paradigm of shared circuit evaluation, where the function to be computed is modeled as a circuit consisting of addition and multiplication gates. Before moving on to this paradigm, let's see what secret sharing is. It has been introduced by P1, so I'll briefly go over it. So in order to share some secret, a party picks a random t-degree polynomial with the constant term being the secret. And this polynomial is now evaluated on n publicly known points, where the value S1 to Sn denotes the share of the parties P1 to Pn. So we use a square bracket notation to denote a value S has been secret shared among the parties. First step in the shared circuit evaluation will be for each party to secret share its input, followed by them maintaining a gate invariant, where if the input of the gates are secret shared, the output of the gate also remains secret shared. And once the secret sharing of the final output gate is computed, the parties can run a robust reconstruction protocol to get back the function output Y. So from the properties of this linear secret sharing, we know that the addition gates are free to compute, or they can be locally computed by the parties without any sort of interaction. But the problem is the expensive multiplication gates. So for this, we use the framework of Chaudhary et al. This framework requires two components to evaluate multiplication gates. The first is a network agnostic VSS, and the second is a network agnostic Byzantine agreement protocol. So from literature, we have the second component with the same conditions that we are designing our protocol in. But network agnostic VSS or verifiable secret sharing is present in the perfect setting, in the statistical setting, but there is no such VSS in the computational setting, which we are interested in. So from now on, our main focus will be to design a network agnostic VSS in the computational setting. And then using this framework, we can instantiate our MPC protocol. So VSS or verifiable secret sharing states that given a dealer with some private input S that it would like to share among the parties, the polynomial-based secret sharing of its input using a t-degree polynomial. And the goal is to ensure that adversary corrupting up to T parties should not learn the dealer's secret S. Further, if the dealer itself is corrupt, it could so happen that it distributes some random values to the parties, which might not lie on some t-degree polynomial. And which is why we add an additional layer of verification on top of this polynomial-based secret sharing to ensure that even if the dealer is corrupt, there will be some t-degree polynomial on which its secret is shared. So this is the sharing phase of the VSS protocol. And once this is over, the parties can pool back their shares by running a protocol to reconstruct back what was shared during the sharing phase. So this is the reconstruction protocol. So the goal of a VSS is to ensure that it can allow a dealer to verifiably share its input S such that the following properties hold. So the first is the privacy property, which means that the adversary should not learn the dealer's secret S. Second is the correctness property, which means that if the dealer is honest, the reconstruction protocol should indeed output the dealer's secret S. We have the termination property next, which means both the sharing and reconstruction protocol should timely produce the output. And finally, we have the commitment property, which is for a corrupt dealer, and it states that there should be some value S start, which is reconstructed at the end of the reconstruction protocol. So in order to design our VSS protocol, we use commitment scheme. So it is a protocol between two entities, a committer and a verifier, where the verifier on having input M basically picks an envelope. He will see this message inside the envelope, and this will be sent to the verifier. Sorry, the committer sends it to the verifier. So this is the commit phase. Note that here, the verifier only receives the commitment and not the actual message. Later, when the committer reveals the message along with the opening information, the verifier will be able to check whether the message contained inside the envelope is the same as sent by the committer or not. And depending on that, it can accept or reject the message. So this is the open phase. And we want certain properties from any commitment scheme. The first is the hiding property. So it states that if the verifier is corrupt, it should not happen that in the commit phase, it learns the message of the committer. And the second is the binding property, which means that if the committer is corrupt, it should not happen that later in the open phase, it reveals some different message, which was not committed during the commit phase, and it should be rejected by the verifier with a very high probability. So we use the Pedersen's commitment scheme in our protocol, which is based on the hardness of discrete logarithm problem. But in general, any scheme which satisfies the homomorphic property will work. So this property states that if you have commitments on two messages, M1 and M2, and if you want to compute some linear function of M1 and M2, you can get the commitment on this linear function by simply using those two commitments. So before designing our network agnostic VSS, let us look at a synchronous VSS and an asynchronous VSS protocol. So a synchronous VSS protocol will work with the condition t less than n by 2, or when half of the parties can be corrupted. So here the initial steps remain the same, where the dealer does a polynomial-based secret sharing. And the interesting part is to see how the verification is done. So in the synchronous case, dealer makes use of the commitment scheme, where it will make public the commitment on the coefficients of its sharing polynomial. So there will be t plus 1 commitments. And now each party will be able to verify whether the share it has received is consistent with the commitment or not. So if the share is not consistent, a party can broadcast not okay message or a complaint against the dealer. Now, if there are more than t complaints in the system, we can discard the dealer and output a default sharing, because if there are more than t complaints, then there is at least one honest party who is not okay with the dealer, stating that the dealer is corrupt. Otherwise, dealer now looks for all the not okay parties, and it will broadcast their respective shares. So it will broadcast SI and SN in this case. And once dealer has broadcast this, every party will be able to verify whether the share that it has broadcast is consistent with the commitment or not. So it's easy to see that this protocol achieves the properties of VSS, which mainly follows from the properties of the underlying commitment scheme and the polynomial-based secret sharing scheme. So now we look at an asynchronous VSS protocol. This works with the condition t less than n by 3, or when up to a third of the parties can be corrupt. So here, unlike the synchronous case, the dealer can't pick a univariate polynomial to do the sharing, because there are no such strict timeouts here, and certain number of honest parties may be excluded from the protocol sets. So which is why dealer picks a bivariate polynomial of degree t in both the variables. And now the share of each party will be a univariate lying on this bivariate. So the next steps are similar, where dealer publishes the commitment on each of these univariate polynomials. And an interesting property about a bivariate is that any two parties, Pi and Pj, will have a point Fij in common. So this is the pairwise common point between two parties. And each party, upon receiving the commitments and the shares, they will check for two conditions. First, whether the share that they have received is consistent with the commitment or not. And second, whether the pairwise consistent check holds for every pair of parties or not. So if these two conditions are satisfied, a party will broadcast OK message. And depending on the OK messages, the dealer will now look for a set of size at least n minus t, which we denote as the core set. So these parties are the ones that are publicly confirmed to be okay with the dealer sharing. Now, once dealer has broadcast this core set, we are guaranteed that it will contain at least t plus 1 honest parties because of the condition t less than n by 3. And these t plus 1 honest parties will uniquely define the dealer's bivariate. So using the help of this core set of parties, we can also help the non-core parties to get back their univariate by using the pairwise consistent points. So each core party will send their pairwise common point to the non-core party which they will be able to interpolate and get back their univariates. So now we'll look at our network agnostic VSS, which works with the condition TA plus 2TS less than N. So here we'll follow the same idea as the asynchronous case because parties are not aware of the network type and the delays can be as per the asynchronous case. Additionally, each party here keeps a local clock maintained where it will keep a track of the time as and when the protocol proceeds for it. So now the degree of this bivariate polynomial will be TS in both the variables because TS is the maximum number of corruptions that can happen in a synchronous network. So the steps are same now, and note that if the network is synchronous and the dealer is honest, all the steps will happen timely for an honest party, which means every honest party will receive the commitment from the broadcast of dealer at time TBC, where this time denotes the time for a broadcast. So each party now checks for the same two conditions and they broadcast OK messages, based on which now dealer looks for a set of size at least N minus TS, because TS corrupt parties in case of a synchronous network might choose to not participate in the protocol for a honest dealer. So once dealer has broadcast this core set at time 3 TBC, which will definitely happen for a honest dealer in a synchronous network. But if the network is actually asynchronous, different parties might have different view regarding the core set. Some might have received it while others might not have. So at local time 3 TBC, we ask each parties to participate in an instance of the network agnostic BA protocol with input 1 if you have received the core set, with input 0 otherwise. So this BA protocol can produce two different outputs, whether the core is not found or if the core is found. Now, depending on these two outcomes, the protocol can take different directions. So the first case is when the core set is found or the output of BA is 1. So in this case, we know that a core set of parties is agreed upon, size N minus TS. So what if we ask this core set of parties to help the non-core get the shares as we did in the asynchronous? So will this idea work in the network agnostic case? So it will work if we are guaranteed that the network is asynchronous, because in that case, we will have sufficiently many honest parties in this core set, which will be able to help the non-core parties. But if the network is synchronous and the dealer is corrupt, there can only be TA plus 1 honest parties in this core set, which are not sufficient to define a TS degree bivariate. So which is why we ask the dealer to perform a secondary sharing or a fresh sharing of the shares of the non-core parties, but using a TA degree polynomial. Now, why TA degree? Because if the dealer is honest and the network is synchronous, all the honest parties will be a part of this core set, and adversary anyways knows the share of the non-core parties. And if the network is asynchronous, the TA degree polynomial will indeed maintain the privacy. So steps are now same, where dealer sends the shares for all the non-core parties and makes public the commitments. Each party will check for the consistency and broadcast OK message. And based on the OK messages, dealer will look for a set of size at least N minus TS, which could be different from the original core set, which is why we call it as a qualified set. And note that in either of the networks, this qualified set will contain at least TA plus 1 honest parties, which are sufficient to define a TA degree polynomial. So using the help of this qualified set of parties, the non-core will get their sharings. And this is how we ensure that all the parties indeed get the share on dealer's polynomial. The other case is relatively simpler, where the core set is not found, because it can only happen when the network is synchronous and the dealer is corrupt, or when the network is asynchronous. So here we ask the dealer to look for an updated core set of size at least N minus TA. And this will eventually happen for an honest dealer in a asynchronous network, because all the honest parties will be a part of this updated core set. And once this new core set is broadcast by the dealer, it will contain at least TS plus 1 honest parties in either of the networks. So the idea will be the same, to take help of new core set of parties to disperse the share to the non-core parties. So this was the idea behind our network agnostic VSS, and we will discuss about the open problems. So the first one is to get a packed version of the network agnostic VSS, which means is it possible to pack more number of secrets or like order n number of secrets with the same complexity. The second is to utilize some kind of trust in the system and follow the same methodology, which means get a VSS followed by getting a MPC. And finally, whether it is possible to improve the communication complexity of our network agnostic MPC, which currently is not at par with the state-of-the-art MPC protocols. Thank you.
Any quick question? Do you have any ideas how to improve the gap again between the
Communication.
Yeah.
Yeah, so one of the ideas is to get a paired VSS. So if you increase a factor in VSS, you get a better factor in the MPC protocol. The other is to use some kind of set of assumptions. So these both basically lead to the third one. So, yeah.
Okay, then thanks.
Thank you.
The last presentation. Laconic branching programs from the Diffie-Hellman assumption, and the authors are Sangjam Garg, Mohammed Hajiabadi, Ihan Miao, and Alice Murphy. Alice is going to speak.
Hi, so I'm going to talk about laconic branching programs from the Diffie-Hellman assumption, and this is joint work with Sangjam Garg, Mohammed Hajiabadi, and Peihan Miao. So laconic cryptography is a subset of two-party secure computation, and so we have two parties, and we're going to call them the receiver and the sender. And the receiver has an input Y, which is much larger than the sender's input X. And the protocol starts with the receiver creating a small hash digest of their input and sending that to the sender, who then creates a response message M, which allows the receiver to compute the desired functionality F of XY. And we have standard MPC security. And the whole laconicism requirement is that this is achieved in only one round of communication, so 2 messages, and the communication complexity will not depend on the size of the larger input Y. So there's been some previous work in this realm. So there's a protocol for laconic private set intersection, which is based on LWE or CDH. And this work that I'm talking about is for laconic branching programs, which can also be based on LWE and CDH. And our work can be seen as a generalization of ABD21 because we can also use branching programs to achieve PSI. And even more generally is a protocol for general functionalities. And this is based on LWE. And one of the contributions of this work is the fact that our protocol is for branching programs, and it's based on an assumption other than LWE, so in particular CDH. And there's also protocols for laconic PSI from pairings and also for laconic oblivious transfer. So I'm going to be talking about branching programs, and just for the purposes of this talk, I'm only going to talk about bit checking branching programs, but our protocol can generalize to more complicated predicates. So a BP is a directed tree that can be evaluated on inputs, and each internal node will encode an index. And you do the evaluation starting at the root, and you check the index of your input with the encoded index. And if it's a 0, you go to the left, and if it's a 1, you go to the right. And you continue down the tree in this manner until you get to a leaf node, which will either be accept or reject. And in this example here, we have, for example, if you evaluated this on 0, 0, 0, you end up at the leftmost leaf, which happens to be a 1, which means accept, and its neighbor happens to be a reject, so that's outputting 0. And these are all of the possible inputs of 3-bit strings. And this branching program, we say it describes this set. So these are all the strings that result in an accept. And so that's how a BP is said to describe a set in this context. And we don't have to have balanced trees. So we could have something a tiny bit more complicated like this, where the unbalancedness of this tree results in having wildcards in the described set. Okay, so I've talked about laconic cryptography and branching programs, and so putting them together, we get a situation where the receiver has a branching program and everything else looks the same. And at the end, the desired functionality is the branching program evaluated on the sender's input. So BP of X, and that will either be a 0 or a 1, accept or reject. And again, just to reiterate, we want to do this in only one round of communication. And by that, I mean 2 messages back and forth. And the communication is allowed to grow with the size of X, the smaller input, and it can grow with the depth of the branching program, but it cannot otherwise depend on the size of the branching program. Okay, so I've explained the setup of what we want to do. We want to realize that protocol, that functionality, and our protocol is going to be based heavily on garbled circuits and hash encryption and how they work well together. And then after I explain that, I'm going to go over the construction at a really high level. So I assume everyone is familiar with garbled circuits, so I'm going to go over this pretty quickly. So garbled circuits have a garbling evaluation and simulation algorithms. And the garbling algorithm will take in a circuit, output a garbling of that circuit, and a set of labels. So if you have n input wires, you have 2 n labels. You have a row of 0 labels and a row of 1 labels corresponding to the value of that input wire. And if you want to evaluate a garbled circuit, it takes n labels, and the labels you choose will depend on the bits of X, where X is the value you want to evaluate the circuit at. And the simulation algorithm is for defining security. And the important part about security for the purposes of this talk is that security, as you can see on the left-hand side there, only holds if you have 1 label per column of the garbled labels. So in particular, if you happen to have the label for the input wire 1, the first input wire, and you have the 0 label and the 1 label, then there's no guarantees for security. Okay, and hash encryption, I'm going to go over a bit more slowly because it's a bit less common. So it consists of 3 algorithms: a hashing algorithm, hash encryption, and hash decryption. So encryption is done with respect to a hash value, and you can think of this sort of like a public key. And decryption is done with respect to the pre-image of that hash value, and you can think of that sort of like a secret key. So the first algorithm is the hashing, which behaves just like a collision-resistant hash function. And the encryption algorithm, as you can see in pink, it's being done with respect to a hash value. But the encryption payload is a bit unusual. It's a matrix of 2n messages. And as you can see, the decryption here, again, it's being done with respect to the pre-image of the encrypting hash value, so it's X. And the decryption is only decrypting half of the payload. In particular, it's decrypting the half that depends on the bits of the pre-image X. So the payload messages, that matrix, only 1 message per column is being decrypted, and which message that is depends on the bits of X. So the security says basically that the message in the column that is not decrypted, it remains secure as if you never decrypted at all. And so one thing about this is that it is not public key encryption. That's why I said you can think of it like a secret key and like a public key, because they are different. So in public key encryption, if you have the secret key and someone sends you a ciphertext, you can decrypt the entire payload of the encrypted message. But in this case, you cannot. Even if you have the correct secret key, you can only decrypt half of the encrypted messages. So I'm going to just go through a really quick example of a concrete example. So here the sender has a 4-bit string and they hash it and send that to the receiver. And they are encrypting these 8 messages. And they're highlighted in red to indicate that they are encrypted and they are hidden. And they'll send this to the sender, who then decrypts with their pre-image X. And so the decryption is going to be done according to the bits of X. So only 4 messages are going to be decrypted. And as you can see, those match the bits of X, and the remaining 4 messages are secure. And the sender cannot get them, can never get them, because of collision resistance. So they're never available to the sender. And the hash encryption primitive can be built from the Diffie-Hellman assumption or LWE. And as you may have guessed, garbled circuits and hash encryption are going to work really well together. So as I said before, garbled circuit security only holds if only one label per column is known. And hash decryption only reveals one message per column. So if we hash encrypt garbled labels, the decryptor will only learn one garbled label per column, which will allow them to evaluate while maintaining security. Okay, so now I'm going to go over our construction at a high level. So just to reiterate, this is what we want. This is our laconic branching program setup, where the receiver has a branching program and the sender has a message. And we want the receiver to learn BP of X with only 2 messages. And we don't want any of the messages to have a size that depends on the size of the BP. So we're going to look at this concrete example where the receiver has a depth 1 branching program and the sender has the string 0, 1. So first, what's going to happen is the receiver will do this sort of Merkle hash style hash of their branching program. So it's going to be hash of the root, left child, right child, and send this to the sender. And so in the end, if you look, because the second bit of the sender's string is 1, and if you evaluate that on the BP, you check the second index and that's 1. So in the end, we're going to want the output of this to be reject. So next, I'm going to go over what the sender actually sends to achieve this. So the sender doesn't know what the receiver's BP looks like because we want security for the receiver. So the sender does know that it has depth 1. So consider this generic depth 1 branching program, which checks the ith index and goes to Q sub 0 or Q sub 1. So left child, right child. So the sender is going to define this function f, and it has its input x hard coded. So that's what I mean by the square brackets. And it has 3 inputs. It takes an index, j, and then 2 possible output values, q sub 0 and q sub 1. And we'll output the q that corresponds to the jth bit of x. So let's consider what would happen if the receiver was able to evaluate this function on input that matches their branching program. So the root value, the left child, and then the right child. So what would happen is that if the second bit of the sender's input was 0, it would output 1 because that's what this Q sub 0 is. And if it's 1, then it would output Q sub 1. And we see because of the values of everything, because QS is 1, it will output 0, which is what we wanted. That's the desired output. That's what BP of X will equal. So it would be really great if the receiver could evaluate this function. But the thing is, it has X hard-coded, and we want to keep X secret from the receiver. So what we'll do is we'll follow Yao's garbled circuit protocol to allow the receiver to evaluate this without seeing the hard-coded value. So how this works is, first, as you will recall, the first message in the protocol was the hash value, this hash value. So this will be sent over, and the sender will do a garbling of F, and then they will hash encrypt the labels, the garbled labels resulting from the garbling, and the public key that they will use for the hash encryption is the value sent by the receiver. And they will send over this hash encryption and the garbled circuit. Then the receiver will just hash decrypt this with their secret key, hash secret key, which is Z. And the result will be the labels, the garbled labels associated with the bits of Z. And if they put this in the garbling evaluation algorithm, what they get is 0, which is the output we wanted. And the reason we get 0 is because doing the garbled evaluation on these labels is equivalent to evaluating the function on the input Z, because we're evaluating the garbled circuit on the garbled labels associated with the bits of Z, which is the same, was equivalent to evaluating the function on Z. And this is exactly what we had in the previous slide. And so that's why we get this output 0. Okay, so that's depth 1, which is a very simple branching program. So what would happen if the receiver's branching program was depth 2? So we might note that we have 2 instances of a depth 1 branching program. So what if we send 2 hash values to the sender? And the sender does the same thing they did before. They create 2 hash encryptions this time of the garbled labels, and they send those over. But the thing is, we've already run into 2 problems. And the first one is the fact that sending over these 2 encryptions of the labels will destroy garbled circuit security, because we have 2 encryptions of the same labels under different hash values. So that doesn't work. And we also have a problem with the size, because we're going to have a size blow up, communication cost blow up, because we're sending, the number of hash values we're sending will depend on the BP beyond just the depth of the BP. So this doesn't work. And what we're going to do is we're going to use deferred encryption to solve this problem, which will involve another garbled circuit, which will allow the encryption to happen on the receiver's end, depending on the receiver's BP instead of on the sender's end. So I don't have time to go into it, but it's in the paper if you're interested. Okay, so the main contributions of this paper are giving a new construction for laconic 2PC for branching programs from LWE or CDH. And in particular, it's the first construction for laconic branching programs from an assumption other than LWE. And this work can be seen as a generalization of ABD 21, but not as general as the fully general construction. And another thing is we can realize private set intersection and also private set union with the branching programs. And also because we allow for unbalanced branching programs and wildcards in general, we can allow a receiver set to be expressed more concisely. Thank you.
the performance of represent section. So how would the performance change, or what would be if you use the current constructions that you are planning to use?
For PSI, if you want to use branching programs to do that, you would create a branching program that describes the set, as I mentioned, and then you would just use that. And so if you have the BP that describes your set, you can use that to realize PSI. And PSU is actually really similar, where you just actually flip all of the leaf nodes. So if it was accept for PSI, and you flip it for PSU to be reject, and it's the same otherwise.
And will it give a difference from the state of the art, or, you know?
Yeah, in some cases it can. In particular, some of the, depending on, as I mentioned with the wildcards, like you can express sets more concisely. So in those, in that case, it would be an improvement. And the fact that we don't, the previous works that had some similarities in the construction did not allow for unbalanced trees, like, because you had to build a tree in the protocol anyway. So in that case, there would be an improvement.
Question.
Meaning that basically will be able to get your structure and head cushion similar
Sorry, I don't think I caught that.
Okay, so like if you get head cushion and body circuit, like also need put it together and get like your country.
Oh yeah, yes.
Would like to add?
Oh, yeah. So the main the reason our protocol works from CDH or LWE is like exactly because there are constructions for hash encryption for LWE and CDH. So yeah.
Thanks,